Welcome back, folks, and the topic for today's video is going to be information about how and in what order to fill atomic orbitals with electrons. Alright, so we know that when we're dealing with multi-element, or rather multi-electron elements, we're going to have to deal with more than one electron. So as a result, we have to figure out what order in which we're going to place those electrons into the orbitals and which orbitals are going to accept those electrons. Alright, so I'm going to basically begin this and also limit the discussion for today to just two principal energy levels. Okay, so we can see here that we have the n equals 1 energy level, and over here I have the n equals 2 principal energy level. Okay, so these correspond to the n equals 1 and n equal 2 principal quantum numbers that we talked about in class. And of course, within those, we know that we have some number of orbitals that we can work with. Okay, so for the n equals 1 level, we only have a single s orbital. But if we go up to the n equals 2 level, we have a single s orbital, but then we gain a set of 2p orbitals. 2px, the 2py, and the 2pz, as we discussed in class. Alright? So now, if we're talking about fairly simple elements with few numbers of electrons, this will give us enough orbitals to work with. Then when we get to class next time, we can look at how we can continue to fill electrons in to orbitals well beyond this for the heavier elements that have lots of electrons. So we'll just start here to keep things simple. So we have some basic rules that apply all of the time. First rule, we only will populate a single orbital with up to 2 electrons, no more. Okay, so I can put 1 electron into an orbital or 2 electrons into an orbital, but no more than that. Next, the rule says that we fill our orbitals from low energy to high energy. So we always start with the low energy orbitals, and then we continue to fill the orbitals from low to high until we run out of electrons. The third rule is probably the toughest to remember. If we have greater than 1 orbitals at the same energy, we're going to distribute the electrons among those orbitals, and then we're going to come back and pair the remaining electrons back into those orbitals. So with an s orbital, we don't have to worry about these because we see that these are 2 s orbitals that lie at different energies. However, by the time we get to p's or d's or f's, what we find is that we have a set of 3 p orbitals here, and you'll see that these 3 p orbitals have the same energy. We say that these 3 orbitals are degenerate. What degenerate means in this context is that those 3 p orbitals lie at exactly the same energy. Okay, so the rule is, if I'm going to populate electrons into these orbitals, I'm better off actually putting an electron here, and an an electron here, and then if I have any more electrons left, then I'm going to come back and pair them up in the orbitals. And we're going to see how that works in a real-world case here in just a moment. Alright? So, when we talk about this, there are really 2 ways of being able to describe how we actually put the electrons into the orbitals. The first is by way of what we call an electron configuration, and the second is by means of what we call an orbital diagram. And we're going to demonstrate for 2 elements what those 2 schemes look like. Alright, so let's start out with something really, really simple, like a lithium atom. Now, if you go to the periodic table and you look up lithium, you're going to find its element number 3. That means lithium has 3 protons in it, and it's got 3 electrons in it. Okay, so I know how many electrons I'm dealing with. I gotta house 3 electrons here in the case of lithium. So if we follow our rules, we're going to start from the lowest energy, we're going to go to the highest energy, and we're only going to populate each orbital with 2 electrons. Okay? Now in the case of the electron configuration, I'm just going to list the orbitals by name. So here's the 1s orbital at the lowest energy, and then according to my diagram here, the next place I need to go is to the 2s. Now I don't have to go any farther than that because I only have to house 3 electrons, and these 2 orbitals together can house up to 4. So that's as far as I need to go. So here's what I do. I'm going to take my first 2 electrons, and I'm going to put them into the 1s orbital. So I'm going to represent that as a superscript 2 above the s. Then I have 2 more electrons to work with. So, or sorry, I think it's just 1 more electron to work with, isn't it? If I'm dealing with lithium, I've taken care of 2, I just need 1 more. That next electron is going to go to the next highest orbital, which according to our diagram is the 2s. So I'm going to put a 2s 1 there. Okay, so I've accounted for all 3 of the electrons in lithium. 2 in the 2s orbital, and 2 in the 1s orbital, and 1 in the 2s orbital. So I think we're good there. So that's a typical electron configuration. Now we can also do what's called an orbital diagram. The orbital diagram actually tells us a little bit more information about the system because it tells us something about the electron spins and the order in which we're going to place those electrons into the orbitals. So now what I'm going to do is I'm going to represent each orbital as essentially a dash here, and I'm going to show how I'm going to populate the orbitals with the electrons. So in the case of the 1s orbital, I know I'm going to put 2 electrons in there. Now according to the spin quantum number, we know that those 2 electrons have to be in there of opposite spin. One has to be spin up with a quantum number of 1/2. The other one has to be spin down with an m sub s quantum number of -1/2. So I'm going to show that by showing 1 electron going up with an arrow looking like that. That's a spin up. And 1 electron going with an arrow pointed down. That's a spin down. So that tells me that these 2 electrons are in that orbital with opposing spins. All right? So that's important to us. So this way we can show that each one of these electrons, even though it's inhabiting the same orbital, will ultimately have a different set of quantum numbers because of the differentiation in the spin. All right, so now I got to get an extra electron into the 2s. That's where the 3rd one goes. So we'll just put it in there as spin up. I could have put it in spin down as well, but normally by tradition we just start spin up and then go to spin down. Okay, so there's my orbital diagram. Pretty straightforward for the case of lithium. So let's do another one. Let's take a look at oxygen. Now if we look up oxygen in the periodic table, we're going to find that it has 8 electrons in it. So we've got to populate 8 electrons. So if I look here, we got plenty of space. I can put 2 here, put 2 here. That gives me 4. Then I can go 5, 6, 7, 8, 9, 10. So I could put a total of 10 electrons here between the n equals 1 and the n equals 2 levels. So I got plenty of room for those 8 electrons. So what order do they go in? Well, they go in from low energy to high. So I start out with the 1s. I know I can put 2 electrons in there. So I use a superscript 2. Next, I have the 2s orbital. Okay? Single orbital, I can put 2 electrons in there. So that becomes a 2s2. And then that leaves me with 4 more electrons that I have to house in the 2p. And I got plenty of room in there because the 2p's together can house up to 6 electrons. I only need 4. So I'm going to write that in as a 2p4. So now I've got my 4 plus my 2 plus my 2, which is my 8. So I've accounted for all the electrons. Okay, so I have 2 s orbitals that are full, and then a partially full set of p orbitals. So now, the nice thing about the orbital diagram is that's going to show us exactly how those electrons are going to go in there in terms of their spins. So again, 1s orbital. I'm going to put my 2 electrons in there, 1 spin up, 1 spin down. Okay? Then I'm going to go up to my next orbital in energy, the 2s. Again, I'm going to put an electron in there, spin up, another 1 spin down. Okay, so we're satisfying our quantum number requirements here. And then I've got 4 more electrons to put in here. But now we've got to fall back to rule 3 here. Okay? So if I got more than 1 orbital at the same energy, which I do, okay, I got to distribute the electrons first across those orbitals, and then if I need more space, I'm going to start pairing them up. Okay? So here's what we do. I got 4 electrons to account for. So I'm going to bring 1 in spin up here in the first orbital, that would be the 2px. Now I'm going to bring my second electron in to my py, and then I'm going to bring my third electron in to the pz. Alright, now I still need to get 1 more electron in here. So I've distributed first, now I'm going to start to pair. So I'm going to come back and I'm going to put that last electron paired up, spin down, in that first p orbital, which is presumably a px. Alright? Now the reason why we distribute before we pair is because of repulsion. Remember that electrons carry a negative charge, and because they carry a negative charge, they're going to repel each other. So what that means is that if I have 3 orbitals of the same energy, I'm basically avoiding that repulsion energy by distributing those electrons across the orbitals before I then pair them up in the same space. Because if I throw 2 electrons into the same space, they're going to repel each other, which drives them both to a little bit higher energy. So I can keep the whole overall energy of the atom lower by distributing across orbitals first before I then come back and pair up. Okay, so that's the reason why number 3 is the rule that I follow. All right, so in class next time what we're going to do is continue to follow this trend. We'll do more with electron configurations and orbital diagrams, but we're going to show you the order for filling if we're going to go beyond the first 2 principal energy levels. We can then come up with rules to show us how I can populate these orbitals for any element in the periodic table. So that's where we're going to be headed next. So we'll see you then.